that stream in a second. Yeah. I'll tell you. I'm just giving it a thumbs up on something quick. Yeah, I'll be watching live. Oh, it's live? Do you need to make the... Do I make the scene switch? All good? Hi everyone, welcome to week 4. Today we've got a talk by Dr. Chung, robots in human spaces. Please give everyone a applause.
Thank you, and thanks to you, Mars, thanks Jay for inviting me to present to you guys. I'm pretty excited to actually meet all of you because I've actually just started at UQ a few months ago. So I'm getting a feel for the lay of the land and what the general robotics landscape looks like at the university. I'm happy to contribute to this as well. So to begin, I want to acknowledge the traditional owners of the land on which we meet. This is the Yagara and the Turrbal people. I want to acknowledge their custodianship. And I want to pay my respects to their ancestors, past, present, and emerging, and who continue a cultural and spiritual connection to country. I recognise their valuable contributions to Australian and global society. Now, I've had the privilege, I've had the luck to work in research labs all over the world. And for the last, I would say, close to over 8 years of my career, I've been able to work over the US and in Europe. And as someone who's grown up in Australia, I do understand the pull of home and community and country. So it gives you a little bit of a taste of what it's like to feel the pull of your home when you go out and you work in other places. So I'm here to talk to you about robots in human spaces. And the one thing that I want to say up front is that this is not work that I've done alone or by myself in any way, shape or form. This is definitely work that has been extremely collaborative, and it's largely work that I did in my previous role as a senior researcher in the Autonomous Systems Lab at ETH Zurich. So you see a picture of us back in 2019 during our Christmas celebration, and then again in 2022 when we were having our summer gathering. I couldn't find any other group photos of us in between. I don't know what happened, but there you go. Between 2019 and 2022, it was a very large lab, over 50 people who are working in there. And all these people have contributed in some way to the ideas that I'm going to present to you now. So just to give you an idea of what I'm talking about when I'm talking about robots in human spaces. So this here is our Royal Yumi mobile manipulation platform. So it consists of a dual-armed ABB Yumi robot, and that's mounted on top of a Ridgeback ClearPath platform. And we've equipped it with a number of different sensors. So first of all, we have localization sensors, which allows it to understand where inside our office it happens to be at any particular time. And we've also equipped it with an RGBD sensor, which we mounted on the wrist of the robot. And this is the sensor that we're going to use to do a lot of the object detection and understanding of the scene. Now, the task that we've given to Royal Yumi in this particular case is we want it to go and find a banana in this environment, fetch it, and bring it back to us. So what you're going to see is the RGBD camera that's mounted on the wrist. You're going to see the camera stream that's coming from there pop up in the bottom right-hand corner in just a moment. And you'll see that the target object we've placed on top of that table over there. Now, as Yumi moves across this scene, it will occasionally detect where that banana is, and it will detect it over multiple images. And what that allows it to do is to triangulate where that object is and place it inside its map. So you see over here, this yellow dot is where it understands the target object to be in the 3D position inside its space. Because of that, it's able to use its motion planning algorithms to navigate to a position in front of the banana. And then once it arrives, it now needs to have a dense understanding of what's going on in front of it in order to be able to grasp that banana. So here it moves the camera, which is mounted on its right-hand wrist, over the scene. And what that's going to allow us to do is to stitch together a dense point cloud of what's going on in front of the robot. And you see that in the bottom left-hand corner. What we can do is we can pass that point cloud to one of our grasp synthesis algorithms, and that will allow us to decide where the hand can be placed in order to try and grasp this object. So in this case, it's detected a grasp, but unfortunately, because Yumi's trying to grab it with its left hand, it can't actually reach it. So we need to scoot the robot over a little bit. Once it's in its new position, it's got to repeat those last couple of steps. So again, get another dense point cloud, pass that point cloud through the grasp synthesis algorithms, come up with a grasp, as you see down there, and go and actually execute that grasp. So now it's successfully grabbed the banana, and all it really has to do now is sneak back to the person who's actually asked for that banana to be delivered and actually go and hand that over. So there's quite a lot of stuff going on under the hood between where the raw sensor information comes into the robot and how it decides what action it's supposed to take inside the world. So we have several things. First of all, the robot needs to know where it is inside its space. It needs to be able to localize. It also needs to have a perception system which is able to tell it that, for example, this blob of pixels represents a set of dishes that it might have to interact with, whereas this other blob of pixels over here represent a table that it shouldn't run into. So we need a perception system that's able to give us some understanding, some representation of that physical environment that the robot is in. Now, with that perception information, we need to then have some interaction. We need to be able to decide how the robot should safely and physically interact with those objects, whether it's something that it should avoid running into or if it's something that it physically needs to go and touch and interact with. And to string all of these pieces together, we also need to be able to plan which of these actions needs to happen and when. We need to do motion planning. And because we're talking about robots in human spaces, occasionally there's also people floating around, and you need to be able to know how you actually want to move around in those spaces to maintain safety and all these other kind of critical things. So this is quite a lot of stuff, and I realize I'm the thing standing between you and pizza, so I'm going to cut down what we're going to talk about today and just focus on these three elements. So just the perception, the interaction, and the planning. We're going to leave localization for another day. So let's take a look at how we do perception. So your traditional robotic perception pipeline will include some information coming in from your RGBD camera, in this case, which you can see on the left. So in your first column, you have the color information that's coming in as a video stream. And then in the second column, you have your depth information, which tells you 3D information of the environment, how far away surfaces are from where the camera is. Now, traditional methods for stringing this information together into one kind of physical representation that you can use will generally put it together into some sort of scene reconstruction, something which just tells you where the surfaces are altogether. Now, besides encoding how this room looks by having the camera waved around, we don't really get a lot more information from that, right? We don't get to see that, for example, this thing here is a chair. Not only is it a chair, but it's not actually stuck on the ground, that if you were to push it and move around, it would move separately to the ground. So in a representation like this, where we're just looking at surfaces, there's no higher level abstract understanding about what's actually in the environment and what you can do with it. So what's more useful for a lot of robotic applications that we're interested in would be a representation that encodes knowledge about the individual objects that are actually in this space. So for example, if we're talking about grasping and manipulation, we need to know that there are bowls that are on the table, not just bowl, but that there are individual, distinct and separate bowls. And perhaps, your user might be saying, I want you to grab a specific one. So knowing that they all move separately to one another, that they are supported by the table but not attached to it, these are all kinds of extra information that we would like to have in order to be able to make long horizon plans and get our robots to actually do something useful. So this task of mapping at the level of individual objects and individual instances of objects is what we call instance-aware semantic mapping. And so first of all, if we just look at scene geometry, so remember we have RGB and also depth. So depth gives us geometry. From that piece of information, we can already do quite a lot in terms of being able to understand what objects are. So if you think about from an individual frame, when you're looking at the 3D depth from the camera, we can already make some assumptions about what an object is and what an object is not. So in this case, the first kind of most conservative guess that we take is to say things which are convex. We're going to consider things which are convex to be the minimum requirement for being an object. Because typically, if it's convex, you don't expect it to, break apart. And most of our objects are made up of at least small convex pieces stuck together in some way, shape, or form. So from a single image, you can already start to do segmentation just based on that kind of geometry information. But remember, we're not just taking one image. We have a robot which is moving this camera through the space. So we get a whole stream of images, which means that we can actually stitch together sequential frames in order to be able to put all these partial observations together to get more complete models of all the objects which are in our space. Now, what you'll notice is that there are these three faces which are popping up on the side. So these three people, Margarita Grimwald, Fadri Fura, and Tonchi Novkovic, they're the main contributors to this work. They were the PhD students who worked on this. They've now since graduated and gone off to work in wonderful startups and meta industries, all these kinds of things. But I wanted to acknowledge that these are the people who were contributing mostly to this scientific work. All right, so we're talking about geometry, just looking at geometry. Now, what Margarita, Fadri, and Tonchi came up with was the Incremental Object Database, or IODB. This is how you can build up, from moving your camera in the scene, an idea of all the different objects which you've seen over time. So what you're going to see in this video, in the top left, over here is the raw depth information, so just what the camera is seeing at every frame. Underneath it over here, you'll see the instance segmentation. So for that frame, just using geometry as a rule for deciding what is an object and what is not, this is how we are going to segment. So each of these different colors, they're going to flash around a lot, but you'll see that we're separating surfaces from one another. Now in this main section, what you'll see is the full reconstruction of that scene. And occasionally, what you see in color is going to be the current viewpoint of the camera. And occasionally there's objects going to flash green. And every time it flashes green, it is indicating that what is currently seen is being integrated into an object that it has stored in its database. So let's take a look. So this data was actually collected using a Google Tango, if any of you were around to remember that device. It was actually quite a useful sensor for us because it gave us very good pose information for the camera itself. It had very tightly integrated IMU with the camera information. And that allowed us to basically just move the camera around and trust the pose information that was coming back out to tell us exactly where the camera was when we were taking each one of these viewpoints. So as you can see, as we're moving around in this space, each of these individual segments are slowly being built up. And what's really nice about the fact that we're keeping a memory, a database of the things that we've seen in the past, is that we can do a couple of extra checks. So on the left, you see our cow. The radio that we had in our office was, for some reason, a cow, but I guess it's Switzerland, so that kind of makes sense. And green are points which are matching very nicely to the model that we had in the database. So you see there's a lot of green on the cow, that's wonderful. It's also quite a unique shape, so we can trust that this is probably a good match. Now on the right-hand side, you see an armchair, and you see this kind of cylindrical object which has been matched to the arm of this chair. Now initially, when we're just doing the match kind of in abstract space, where we have our object and we have the thing that we've segmented and we're saying, do these two things fit? There's quite a lot of good overlap. So you see there's quite a lot of green over here. But this cylindrical object doesn't just exist in nebulous space, it exists in our scene. So what we can do to check if these two things truly match is to take that model that we had in our database and actually put it back into the scene. So now we're saying, if this really was part of the armchair, could we actually fit the armchair back into the environment where we saw the cylinder? And what we discover is that the answer is no, right? The chair would go through the floor, which is no good. It also ran into some other objects in the scene, and we should have seen other parts of the chair. So with all this additional contextual information, it means that we can actually say, actually, these two things don't match, and then avoid merging things which are not supposed to be together. Okay, so that is what geometry gives us. That's what depth information gives us from the camera. But we also have color information. We also have RGB information. And this is actually quite a complementary piece of information when compared to the depth information. So first of all, you see down the bottom the depth images. So this is what we were getting just from IODB from the last slide that you saw. And this gives us a lot of nice, crisp, clean edges because geometry, this is exactly what we are measuring. But what you notice is that it tends to over-segment. So this one chair is now chopped up into 4 different pieces. You've got the cushion, you've got the back, you've got the 2 arms, they're all separate, right? And ideally we would like to connect all of these things together because if we want to tell the robot to move the chair, we don't want to have to tell it to move which piece of the chair, right? We expect all of it to move together when it moves. So that's what geometry is giving us, and that's kind of the limitation of geometry. It oversegments. Now, on the other hand, we have color information, and we have state-of-the-art pixel-wise segmentation algorithms that can give us not only good semantic labels of what it is that we're looking at, but it can also avoid this kind of oversegmentation. So you have things which is trying to say, okay, this whole thing over here, this whole blob is chair. What its limitations are, however, is that it's not very good at finding those edges. So you see the edges are a bit wobbly here, they're not so crisp. So bringing together the color information and also the depth information means that we can actually get the best of both worlds. And so looking at this example where we're testing this algorithm out on a data set where the camera's being moved around in this room scene, you can see it, once again, you've got the instance-aware segmentation going on down the bottom. The mask-CNN, which is our semantic segmenter at the top, doesn't segment everything in the scene, right? Because it doesn't have labels for everything that it's looking at. Only a specific subset of things has it ever experienced or been trained on. Now, the geometry doesn't suffer from this, right? Geometry doesn't care what it's looking at. It just looks at normals and it tries to do some sort of comparison based off of that. So when we bring these two things together, it means that we can segment everything, first of all. So the geometry allows us to segment everything. And then the color allows us to group parts together which belong semantically to a single object. And so you can see up the top, we have the semantic map. So just the things that are labeled. It's missing quite a lot of the scene, actually, because there's not actually a good understanding of what a table is, for example. Some reason it hasn't been labeled in this data set. And then down the bottom, you have the geometry. So if we look at the results of what this scene is, what combining RGB and depth information can do, we can have a look at some case studies. So first of all, bringing these two streams of information together means that we don't just have bits of chair, but we have whole chairs, and they are distinct chairs. So not just chair, but chair 1, chair 2. Secondly, we can actually segment stuff that might not even have been picked up by the person who was doing the labeling. So if you look at this weird little blob that's sitting on top of the table, the depth segmentation is able to distinguish that actually this is very unlikely to be part of the table, that your table shouldn't generally have lumps, and is able to segment that out of the scene for us, even though in our ground truth, this is not something that the person has picked up. So what we were looking at before was on a data set, so we could run all this stuff offline. But because we like to put things on robots, now we have to consider whether or not this is going to work online on a real robotic system. So now we're bringing back all those constraints. Do we have the computation? Do we have the bandwidth? All this kind of stuff. Is it all going to work? So in this example, we bring back Royal Yumi. This time we have a slightly different camera setup. So you'll see that it has two RGBD cameras, the two prime sensors, one looking forward and one looking down. And this was mostly just so that we can get a larger field of view for this particular experiment as we drove it around our office. So you'll see this is running online now. Our algorithm runs at roughly 1 Hertz, because that's typically the inference rate that you're getting out of the deep neural network. You can make it go faster depending on some accelerations that you can apply, but it becomes a lot of engineering. But yes, around 1 Hertz is what we were expecting. And so keep in mind that if your color camera is running at 30 Hertz, what that means is that you are chucking out 29 of those 30 frames. So you're only using 1 every second to be able to build this up. So it's not going to look as clean as some of those other examples that you saw before. But the results are pretty promising. What you can see is that it segments out these pieces of furniture. The kitchen is a bit of a mess, but you can see that there's individual bottles and things which are separated out and that are not part of the bench. And yeah, we can confirm that this is a kind of perception algorithm that will allow us to do dense surface reconstructions that give us semantic information as well as instance information. Okay, so with this kind of perception tool, now the next question is, how do we actually go about interacting with the objects that we've identified? So specifically, I want to talk about grasping. Now, grasping as a general kind of research direction can be broken down into whether you're grasping stuff that you already have seen before or stuff that you've never seen before, so known versus unknown objects. So if you know what it is that you're trying to grab, the problem is not so difficult, because either you can do something offline where you can model what sort of force closure grasp will allow you to apply forces that go through the center of your objects. Or online, you can do things like 6D pose estimation to say, okay, I know how to grasp a handrail, and I'm looking at this scene where there should be a handrail in here, what is its current orientation? Once I figure out what that orientation is, I just go and do the grasp that I know that's going to work. So that's if you know what you're trying to grab. Now for us, it's way, way, way more interesting to grab things that we don't know about, that we've never seen before. And in that case, you're now looking at what kind of sensor information is coming in. So if you're just looking at individual frames, for example, if you're just looking at one depth image, then you can only really synthesize grasp in the normal viewpoint to the frame. Right? So in that case, this is what you're seeing on the left here, these kind of top-down grasps. And then if you want to stitch together 3D representations like a point cloud, then you can do 6 degree of freedom grasp, where you can actually grab it from any orientation that you like. Now, what currently existed in the literature, in the community, before we started doing this work, was focused more on sampling-based methods. And what that means is that if they were given a depth image or a point cloud, for example, they would try to work out where they could grasp by chopping up the image or the point cloud into small patches and saying, can I grab this patch? Can I grab this patch? What about this patch, or this patch, or this patch, or this patch? Right? And for us, we thought that seemed a bit silly because it was inefficient in 2 ways. First of all, you're now kind of tied to your sampling algorithm. So if you sample well, or if you're lucky, then maybe you find a good place to grasp. But if you sample poorly, or you don't have a huge sampling budget, then you're kind of stuck. Right? So sampling, for that reason, was unsatisfying. The second reason is that if you're sampling patches, you're throwing away a lot of contextual information, which could be kind of useful in the whole scene. So if you're trying to grab something which is in clutter, and you just kind of chopped out a little part of it and said, can I grab this part? You don't know if there's other stuff in the way, like occluding where your fingers are going to go if you actually go and grab that. So by chopping it out and taking patches was also not that satisfying for us. And so what we wanted was a solution that could avoid both of those things. The other thing is that we wanted to exploit the perceptual representation that we got from the previous work that we talked about. And the scene representation that we used was a truncated signed distance field. So this is a volumetric representation which tells us the distances to all of the surfaces. This seems like pretty useful information if you want to go and grasp and physically interact with stuff. So why throw that away? Let's try and exploit that information as well. So let's see how we do that. This is work by Michel Breyer. He recently defended his PhD at the end of last year, and now is also working in industry, working on a quite interesting grasping project with Amazon Robotics. But this is what he did in terms of trying to solve this 6 degree of freedom grasping problem. You see our setup on the left? We've got the Franca Amica Panda arm, which has a depth sensor mounted on the wrist. And you have the scene of what it's trying to grab in front of it. Now we can reconstruct this scene using our perception algorithms, so we can get our truncated signed distance field. Again, it's a volume where every voxel in that volume tells you the distance to the nearest surface. What we would ideally like is to pass this information through some kind of a black box, and on the other side have 3 things come out. A prediction of the grasp quality for every single voxel in this space. So a question to say, if I was to try and grab at this voxel, what's the probability that I would successfully grab something? And I want that answered everywhere across the volume. So that's the grasp quality. We also need to know what orientation the hand should be in. And again, we're looking at 6 degrees of freedom, so it's not just grabbing from the top, but it can turn at any angle and it can rotate the wrist. And we also need to know how wide the gripper should be open so that it doesn't run into other stuff, but is able to grab the object that we're interested in. And so with all this information, what we want to be able to then extract out of that is where it's most likely to be successful at actually successfully grasping something. Now, I mentioned before that we wanted to exploit the structure that we had from perception. So it's volumetric, and it gives us distances to surfaces. So first of all, off the bat, one of the key things that we can do straight away is to directly filter out spaces that we know there's no chance the robot's going to grab anything. If you know how deep your fingers are, then you know what the minimum distance you need to be away from your surface is, right? So you can filter out everything that's free space beyond that. You know, there's no chance that you're going to grab anything there. That's the first thing that we can exploit from our perception representation. The second thing that we can exploit is the fact that it is a structured 3D volume. It's basically a 3D matrix. And if it's a 3D matrix, it's already in a form which is extremely easy to apply deep learning tools to. So you can apply your favorite convolutional neural network on top of this architecture without having to do any kind of backflips to make the data fit into this kind of learning structure. So because of that, this is what we proposed, is the volumetric grasping network, which is a fully convolutional neural network taking in the truncated signed distance field and outputting each of these three values. Now, if we're going to talk about learning, then we have to talk about data, how we actually get data to train our network. And the nice thing about just looking at depth information, in this case, just looking at geometry for grasping, is that you can actually exploit simulations very well in this case, because physics simulators are actually quite good at giving you data which is very much like the data you would expect to get in reality. So in this case, we simulated a bunch of different types of scenes, ones where we just throw the stuff into a box to give us piles, and ones where we have them kind of placed carefully but in a crowded space. And we basically simulate a bunch of different types of graphs, log the ones that were successful, unsuccessful, and this is what we use to train our network. So given the output of our trained VGN, a volumetric grasping network, we can either use this information raw, but remember, we wanted to just get out a handful of graphs that we thought were going to be successful. So we have to filter this a little bit. First thing we can do is we can smooth the output just using a 3D Gaussian. That way we highlight the areas which are going to be more likely to be successful from our grasp quality output. Second thing is we use the TSDF to filter out free space that we know we cannot grasp anything successfully in. And then we can threshold to just get the ones which are higher than a certain grasp quality. Finally, we can do non-maxima suppression to just get the best grasp for each kind of cluster that we have across our scene. All right, so now you can see it working on our robot. So keep in mind, these are all objects that the robot has never seen before. So they're all random stuff that's never been observed during training. These are all new objects. Now you can see on the bottom right is the reconstruction of the scene and also the color cloud over where it thinks the wrist should go in order to grab something successfully, and also the non-maxima suppression, the final outputs that it finds. So one thing you see down there, oh, excuse me, if I play that again, is at the very beginning, it has to scan the whole scene to get the full reconstruction. So that's before it gets all these. So we tell it to go along this particular trajectory to get enough scans to do that. And every time the scene changes, it's got to do that again. Now, for your viewing pleasure, we've basically removed all of those for the following ones. One, because it takes a long time and it's not that interesting, but do keep this in mind because this scanning trajectory, in order to get what the scene looks like, is one of the longest parts of this whole process of grasping. So it's not perfect. As you can see, sometimes it fails to grab objects. Cylindrical objects are especially tricky, especially ones which are not that squishy but are quite rigid objects. But nevertheless, it is able to successfully grasp things depending basically on how well the network is able to infer the scene. You can also show grasp using full 6 degrees of freedom, not just grasping from the top, but also from the side. And it also works for grabbing very thin objects. So our full reconstruction is still able to get these things even though you have noise in the system. Now, one very cool part of this work is what you're seeing here. The fact that we're just inferring over one CNN means that we can actually run this graph synthesis at frame rate. So we can run it in real time. And this opens up a lot of possibilities in terms of being able to run this in a closed loop system. Okay, so those two things together. Remember I said we had to do the scanning trajectory, and that was one of the longest parts of this whole process. And we can actually do inference at real time at frame rate. So these two things made us think, okay, maybe we can do better, right? Because if the whole goal of this is to grasp an object, It's not to reconstruct the scene. We don't really care about what's going everywhere else in the scene. We just need to know the scene well enough in order to grab the object that we care about. So why waste all that time looking at everything if you already know how to grab the thing in front of you? And so this was motivation for the second piece of work that Michelle did, which is looking at next best view grasp detection. So the idea is that if the robot starts in this pose, and its goal is to grab this box of orange cookies, the ovomaltine cookies there. Now, its first view of the scene is what you see in the top left. It doesn't have a very good picture of where the full extent of the object is, and there's a bunch of stuff in the way. Right? So this is not a great view. But potentially, we could get the robot to move the camera to somewhere else that would give it a better view of the object, a better, clearer view of the object, so that it's able to get a good prediction from VGN and execute that grasp. So this is the idea of next best view grasp planning. So the full kind of pipeline that we have is we've got our robot in our environment, and it's got its controller running at 60 hertz or sometimes even faster, depending on what kind of robot you have. And our robot's able to pass in, first of all, its joint information, so where it is inside the space, and also the camera information, what it's seeing. With that information, we can update the TSDF, the map of this volume in which the target object lies. We can pass that volume through VGN to say, okay, where are the best grasps and how likely do you think you'll succeed at grasping these? And we can use that information to decide whether or not we are confident enough that this grasp is going to be successful. Right? If it is, then we should just stop and grab the object, because there's no point like looking any further. We're already pretty sure that we can grab it. Now, if that is not the case, if you have a very bad view of the target object that you're trying to pick up, then what you probably need to do is go and look somewhere else. And where that somewhere else is you're going to look is going to depend on where your target object is in that scene. Now, the TSDF, again, gives us some very critical information in the way that it's set up. So it gives us distances to surfaces, but what it also gives us is negative distances. So stuff behind surfaces that you haven't seen before are negative. And so that's pretty useful information when you're thinking about where you should look, right? Because if you've seen everything in the positive space, where you should look next is probably the view that's going to give you the most information about the negative stuff that you haven't seen yet. And so that's what you can see colored in these little viewpoints over here. If I can get my cursor here. So over here, the red means you're not going to get a lot of information, but green means we've cast rays from that point, and we're saying, yeah, actually we're going to strike a lot of negative voxels there through our target object. So that's where we should go and place the camera. So we can run this loop, and in fact we can run this loop at however fast we need to do inference and for all of these other things. And we can basically say, well, we're continuously integrating the frames that are coming in from the robot arm, so we're not just going to turn the camera on and off, we're going to leave it on. And as it moves, it can decide at any point to abandon what it's currently doing and just go and grab it, or abandon where it's going and go somewhere else. Right? And we can bring this whole thing into one continuous, online, closed-loop grasping system. And so this is what is demonstrated here. So again, we're trying to grab the box of orange cookies. And this is what you see is kind of the decision-making space of the robot. And so the minute it's able to confidently say where it's going to grasp that object, just cancels all of the perception requirements and just goes and executes that grasp. So you can compare against various baselines, like if you were to just force the robot to always go look from the top, it's going to be much faster than that because we can already make a good decision before we get to that point. And it's specifically going to do much better for cases where looking from the top doesn't actually help you figure out where to grasp something, right? You can figure out maybe it needs to look from the side and so on. All right, so that's something related to how perception and interaction mix together. But I did promise you robots in human spaces. So now when we talk about the planning elements, let's bring the people back. Let's bring the people back into this scene, and let's bring them back in a big way. So one of the other things that we were looking at over at ASL was how do you get robots to navigate in environments that are like this? So this was our open lab day in December of 2019. It's where we get our friends and families, and we get the students to come and they get to see the different types of research that we're doing. Now, we're trying to get Pepper to autonomously navigate across this room. It's just trying to get, it's about 10 meters through the room. And this is a very challenging problem for Pepper. First of all of its sensors for navigation, its LiDARs, are down at the ankle level. And all it's seeing right now are legs, just moving around. Now, traditional path planning algorithms will basically try to look for free space and then plan trajectories through there and execute them. Now, the free space in this kind of a scene is moving, it's fluid. It's not going to stand still and wait for you to make a decision and then go and execute it. The people are wandering around. I mean, Pepper itself is a child magnet, and as you can see, as it moves, there's a cloud of children that follows it and tries to interact with it. And I think it would be extremely bad PR if Pepper ran over a child during one of our open lab days, right? So what sort of navigation algorithm is going to work to get this robot to move across this environment where people are going to try and interact with it, they're going to try and play with it, they might not even notice that the robot is there. There's all these different factors which are making this an extremely challenging path planning problem. Now, for you and me, we don't just freeze when we see a crowd. We're very capable of being able to navigate through a crowd of people, right? Because one thing is that we don't just propel ourselves with our feet through the crowd. We use a lot of other things, like we use body language, we use gestures, we use speech to try and get people's attention. So part of this work was thinking about how do we actually bring all of these other modalities of navigation into robotics to make them far more efficient at being able to navigate around people. So one thing to notice is that, you have scenes like this, and now I'm just showing you what the sensor information look like. So this is what Pepper was seeing on the right here. So the LiDAR is just legs that are popping in and out. You have the depth camera information. It's doing a little bit of segmentation to try and work out where people might be in 3D space and trying to align that to the LiDAR. But as you can see, it's very inconsistent. Stuff is flashing on and off. People are moving. Nobody's just standing still to let the robot figure out what's going on. Now, aside from that, this is kind of one situation that you could imagine robots needing to move around in. But there's a lot of other kinds of human environments, ones where, for example, people are not paying that much attention to the robot. They're trying to get to where they're going, they don't really want to interact with it, and there might be a fair amount of free space for the robot to just go, right? And there could be other scenarios where there's just one person blocking the way. Now, Pepper could decide to make a big circuitous route to get around this person and around all the other obstacles, or perhaps it could try and get the attention of this person and try to figure out whether or not that person is going to let it pass. And so all of this is to summarize to say that, first of all, when you're talking about navigation in human environments, when we get to this kind of level of real-world complexity, there's not going to be one single planner that's going to work for every single type of environment that you're going to see. There's not one behavior that's going to fit. And the second thing is, people, when we are moving around in these kind of spaces, we use all of these other modalities in order to successfully get through. Right? We don't just run ourselves into the free space. We do try and interact with all the other participants who are in this space. So now what we need is, first of all, to be able to elevate our perception, to be able to identify between these different types of cases. So when do we need to interact? When is it okay for the robot to just go? And then the other thing is we need to be able to actually propose what kinds of interactions would work, and then be able to decide when to use which one. So this is the core hypothesis of the work that Daniel here was doing. I don't think I introduced him in the previous slide. Again, Daniel Dugas, defended his thesis middle of last year, and now is actually working at his own startup in Switzerland. So what Daniel proposed was 3 different types of base behaviors, just to test the waters to see whether or not this hypothesis had any legs. So the first kind of interaction mechanism, navigation mechanism that he proposed was called intend. And this one was really the idea that the robot could just navigate with an assumption that the other people in this space, the other pedestrians, were fairly cooperative, but also fairly goal-driven. So everybody else is trying to get somewhere, and if there's any kind of collision avoidance that needs to happen, that both parties are going to help out in that particular collision avoidance action. The second one was to bring in some more of this multimodality idea and to have Pepper actually use its capabilities to speak, to say something. So Pepper in this case would make a verbal utterance. So very politely would say, "Excuse me, I'm coming through." And then it would raise its arms to kind of indicate the direction that it's trying to go. And it would wait for space to free up and then move through that space. And the last one, which we called nudge, again, Pepper is going to make a verbal utterance, this time a little bit more assertive, saying, "I'm passing through, thank you, let me go." It would again raise its arms, but this time, instead of waiting for free space to come up, it's just going to slowly inch its way forward. Right? We had to go through some ethics approvals to make sure that we were going slow enough. But yes, we wanted to make sure that there was quite a kind of firm indication of what it's trying to do in this case. So these are fairly primitive actions, but I think it covered the spectrum of what we were expecting, the kinds of environments we were expecting to place our robots. So this was the starting point. And you can see what each of these behaviors looks like. This is just in 10, so it just goes. Most of the people here are not that interested in reacting to Pepper. For the say scenario, this is where people may not necessarily know that Pepper is there. So it makes a sound, and then you notice it, and then you get out of its way because it's basically asked you to do that. And then finally, with this nudge action, this is for cases where the person might want to interact and be playful with the robot, but if the robot's got a task to do, it's got to go and do that task. So this is using nudge, the most assertive behavior that we have. All right, so with these three, the question now is, which behavior should the robot use and when? So this now boils down to what we used as a partially observable Markov decision process. So we're doing sequential decision making where we don't necessarily know the outcomes of each of our actions, but we have some probability over what we think will happen. Now, in this scenario, for example, your robot's trying to get to that big X down the bottom there. It has a few options of how it can try and move. It can either kind of take the long path around where it thinks there won't be any people, so it can just kind of go and just use its intend behavior. Or it can try and push through the crowd of people if it thinks that it will be successful in doing that, because it might be the fastest way through. Or if it sees that there are places where there's only like a couple of people, that it can try and use the say behavior and get past them that way. Now, in order to make a decision about which one of these actions to use and when, how to string them together, we need a state representation that is going to allow us to distinguish between the outcomes of each of these behaviors. So the useful information is going to involve how crowded the space is, so how many people, how dense is the space, whether or not those people know that the robot is there, so can they perceive the robot, do they understand what it's trying to do, and finally, how permissive the crowd is. So is the crowd going to be polite and let the robot pass, or are they going to be the kind of crowd that's trying to block the robot's way just to see what happens? So these are the three kinds of state variables that we chose to represent our problem and allow us to do this decision making. Now, once you formulate it in this way, you have your transition functions and all the math that sits behind that. What you can use are things like Monte Carlo tree search algorithms that will then allow you to hypothesize, through this particular sequence of actions, which one of these paths is actually going to give me the highest likelihood of getting to my goal fastest. And this is how we can solve for these kind of higher level abstractions. And so we deploy this on Pepper. And you can see it, first of all, working in our office. Now, apart from me, even though everybody else in this office has worked with robots, they were not told exactly what Pepper was doing. So the kind of interactions are fairly natural in terms of how likely somebody is to block Pepper's path, whether they are actually knowing what's going on. And that was fairly successful, so we were confident enough to take it downstairs where we could expose it to more people who don't necessarily see and work with robots every day, so we can get some more interesting behavior. And what was nice to see in these results was this kind of escalation. So Pepper will initially try to intend, and when that fails, it will move to say. And when say fails, then it goes up and it tries to use nudge to get to its goal. Okay, so that was a very kind of rapid fire path through these three different ideas and how we've been using them and the different kinds of research questions that we had between perception, interaction, and planning. And a valid question that you can ask is, where do we go from here? What's next? So one of the things that we were thinking about as a team and that we're still looking at in terms of the broader research goals, even for the robotics community looking at mobile manipulation and robots in human spaces, is this kind of grand challenge. So the mobile manipulation grand challenge that we posed, where you might have a robot in a scene, like a dirty kitchen, for example. You might have multiple robots, and they may be heterogeneous robots, so they might not all be the same kind of robot. And what we would like to be able to do, the way we would like to use these, is we would like to be able to tell them, help me tidy up the kitchen, and just have the team solve that problem for us. That's kind of the grand goal of some of the research that we're trying to do. Now, I put help me in brackets because sometimes, maybe I'm feeling generous and I want to spend my time helping the robots tidy up the kitchen, and sometimes I don't. Sometimes I want them to just figure it out on themselves. And so I want my robot teams to be kind of adaptable to who their teammates are. So whether it's all robots, whether they're heterogeneous in their teams, or whether there's people involved as well. And so this seems like a kind of a domestic problem, but I think it's actually one of the most challenging technical problems that we can try to solve, because there are so many different intricacies in the way that this problem is set up. The fact that we would like to have robots in human spaces, not spaces which are engineered for robots, like you can imagine, like a factory is engineered for a robot. So there's fences everywhere and nobody goes inside, it's just the robot space. But that's not how this technology is really going to have a large impact. It's going to have a large impact if these technologies are flexible enough, are robust enough to work in spaces that they weren't specifically designed for. And that means working in anyone's home. Everyone's home is going to be set up differently. It's going to have different stuff in it. We want this flexibility to be inside of our systems. So if we think about what we're capable of today, right? We looked at some examples of robots navigating through crowded environments, through these kinds of challenging path planning problems. So we've demonstrated this is possible. We looked at how, as these robots are moving through this space, they're able to generate dense 3D semantic segmentations of their environments to understand what's inside that space. So what are the objects, where are the surfaces, where are the walls? We've also shown how robots can use those kinds of representations to then do physical interactions. So you know what's there, you know where it is, and then the robot's able to go and figure out how to go and grasp that. So these technologies also exist. And one thing that I didn't show you today, but was other work by one of my other students, Giuseppe Rizzi, was how we can do force-based interactions. So not just grasping, but applying forces, for example, to open articulated objects like cupboards and doors. So we have all these skills, we've demonstrated all these skills, and we've seen each one of these things happen independently. The question is, why is it still so difficult to bring all of these together to get a robot system to actually go and tidy up a room? Like, why can't I just tell a robot, go and tidy up a room? Now, this was the photo that was taken on my last day of work in Switzerland. So this is my team as of 2022. And what I can say about these lovely people here is that in contrast to our robot, the Royal Panda, all the people in that picture are excellent teammates. They're exceptional. If I was to ask any single one of them to help me tidy up the room, I am very confident that we would be successful. Right? No question. Now, why can't Royal Panda do that? It's not that this robot doesn't have the same physical capabilities as the people in this picture. They are more rudimentary, so its navigation algorithm is not so good, its grasping is not so good, but at the base level, it's able to move without running into the furniture, and it's able to grab stuff, and it's able to understand what's the difference between a laptop and a table. Now, what we hypothesized is that it's not that it doesn't have the physical capabilities. It's actually the fact that the sheer engineering effort that it would take to string together all of these different skills to cover all of the different corner cases that you would expect to see in a human organic environment, the amount of engineering effort that it would take would far outweigh just you and me doing it ourselves. Like, we would just go and tidy up the room, because somebody writing thousands of lines of code to make sure that the robot's always working and never breaks down is going to be much, much harder right now. And largely, we think that this comes down to the fact that you and I understand what tidy means. Like, we know when we say tidy the room, we know implicitly what sets of actions we need to do and what order they need to happen in and what that looks like at the end. Now, trying to explain that to a robot is a lot harder because the robot understands the world in a very different representation. We have spent a lifetime building up a semantic understanding of our environment, and it very compactly defines how we interpret and interact with everything around us. Robots, on the other hand, they interpret the world from their sensor information. So this is pixel intensities, range and bearing measurements. These things don't have abstract meanings, right? This is just numbers. So these are all metric representations. So this challenge that we're talking about in bringing robots to the level of human collaboration is really about translating between our semantic and contextual understanding to their metric representations that they operate in. Now, the motivation for using semantics, first of all, is one, they're human legible, it's the language that we use and we understand how this all works. Two, they're compatible with symbolic planners, so high-level planners that are already being used for a very long time in robotics and in planning, which can solve long horizon tasks. And three, they already include a lot of structure and hierarchy in the way that we use language, and this is something that I think we really should try to exploit. Now, semantics don't solve all problems, so they do have with their own sets of challenges. And just to kind of bring us out to the very end of this talk, let's get some audience participation. So we're going to talk about predicates, so statements of fact. I'm going to ask you some questions and I want you to just tell me true or false, right? True or false. In this picture, is the container, is the Tupperware on the table?
True.
True. What about now?
True.
Still true. Now?
True.
And now?
True.
Great. Is the lid on the container?
True.
Is the lid on the container?
True.
Are you sure? If I asked you to put the lid on the container, I would be very annoyed if this is what you did. I want you to do this when I say put the lid on the container, the one in the middle here. Now, this is not to say that it doesn't always work, because if I was to say, please get me the lid that's on the container, either of those two things is fine, right? It's just when I talk about a specific task, put the lid on the container, that now there's extra constraints attached to it. Now, we kind of understand that, and we don't really think about it day to day, but this is something that you have to explicitly explain to your robot, right? So these kinds of intricacies that we don't really I guess, appreciate all the time because we use language so naturally that when you get to the point of having to explain it to a robot in code and in the metric space that they work in, that you really appreciate how much of a challenge it is to do that translation. And if you were to try and learn these, which is kind of the way that a lot of this research is going, to learn everything exhaustively, it would take you such a long time. And it doesn't feel like the most efficient way to solve this problem because there's already a lot of structure in here, right? If I wanted you to put the lid on the container and you failed, but you understood that this was okay, I don't want the robot to go and explore all the other possibilities of the lid and the container being anywhere in the room. It should just be focusing on those places where this kind of situation, where it's kind of just hovering over the top, was still valid, right? So it should already be able to exploit the structure from the semantics that we've built up in our language. Now, the second thing is that recognizing a predicate to be true or false, like you did, is not the same as knowing how to affect that predicate, how to make that predicate true. So this brings me to the second type of predicate I'm talking about, which is affordances. So if I was to say or ask you, is this banana graspable? This is not a fully formed question, because if you're talking about graspability, you have to ask who is doing the grasping. So if it's Royal Panda and if it's a standard banana, then the answer would typically be yes, the Royal Panda can grasp this banana. But if it was this banana, Royal Panda is never going to be able to grasp the big banana. So we can't just say, Royal Panda can grasp bananas. It's actually specific to the instance. And the way that it fails, or the way that these kinds of predicates fail, will actually give you some information about how you could potentially kind of recover. In this case, either the object that you're trying to grasp has to change or the agent has to change, right? There's no chance that this particular combination is ever going to work. So that's useful information to know. if we're looking at this book, for example, on the table, and we were to ask whether or not it's graspable by this robot, typically the answer will be no, because it's not able to kind of get its stubby fingers around that book to try and lift it up. However, if we look at the book next to it, well, this book is graspable because it's poking out the side, so the robot can actually get its fingers around that and actually lift up the book. Now, this failure case where it can't pick up the smaller one indicates it's not just that it will never be able to pick up that book, but in this particular configuration of that object, it doesn't work. So maybe there's something that it can do, it can interact with it in some way, push it to the side of the table that will allow it to actually grasp that book. And then finally, when we look at kind of the whole scene, if we're asking whether or not the robot can grasp the box of kosher salt at the back, well, if the kosher salt was on its own, yeah, it could grab it, but there's all this other stuff in the way. Now, whether or not the robot can move all this other stuff out of the way is another question, but it relies on there being some kind of interaction with the whole scene, with other parts of the scene, before we can actually evaluate truly whether or not that kosher salt box is graspable by the robot. Okay, so these are kind of the open problems, the open questions, ideas that we're thinking about. And what are we actually doing to kind of solve this semantic to metric translation? Well, there's a couple of different ideas that I want to leave you with. These are research projects that I'm still working with my students back in Switzerland on, and also developing new projects here at UQ that if you're looking for bachelor theses or potentially looking at PhDs, ideas that we will want to explore here. So first of all, we're looking at agent-aware affordance learning. So when we look at individual objects, we want to bring the whole model of the agent back into the question of whether or not something is graspable, pushable, movable, and so on. Not just it's a door handle, therefore you can push it, but if it's this particular robot and this particular door handle, does it work? Secondly, we're looking at object-to-object relationships. So how do we infer predicates just from geometry? So if we're looking at cups and whether or not they can hang, how they can hang, what are the different orientations that will allow us to have certain configurations in the scene. And then finally, if we want to actually go ahead and try to string together these kinds of long horizon tasks, nobody has the time to sit down and code up every single thing that the robot can do. How can the robot automatically extend its understanding of what its skills are and how it relates to the world around it, based on some basic understanding of what it can do? So if we start off with really simple things like, you can navigate, you can grasp things, you can push against things, and you can place things, can you go and explore this environment or hypothesize through some sort of simulation in the background to understand, what specifically do you mean by put the lid on the container and not just on the table? How can you automatically discover these kinds of intricacies? All right, so that brings me to the very end. Again, I want to bring up this wall of people who have been the main contributors to the work that I talked to you about today, also acknowledging all of the research funding that came in to support this work. And yeah, I'm really excited to answer any questions that you might have. Thank you very much.
So we've got a couple of questions from online. The first one is, how does the grasp prediction neural network compare to other neural network driven methods, stuff like dense object nets that came out of CSAIL?
Yes, CSAIL. So CSAIL's from MIT. So dense object nets came out afterwards, after what we did our work on, and it was basically the shifting point between sampling-based methods and regression methods. So ours was a regression method, and dense object nets is the same. So dense object nets is different because they don't just use geometry, they were also looking at features in the space. So they were doing something far more complex. We were just looking at geometry and just trying to figure out based off of that. And I believe dense object nets, it has a similar architecture, I think largely convolutional, fully convolutional, but I believe they go through like a feature layer when they're trying to figure out more specifically maybe information that we were not tapping into. That's kind of my broad understanding of how dense object nets works. Mm-hmm.
Thank you. To me, doing instance semantic segmentation is a lot of effort. Was there any attempt to use segmentation output as a heuristic for the grasp prediction step? Example, the predicted grasps for the harder cylindrical objects might be more predictable if the neural network used that information.
So knowing that it's cylindrical and having
Yeah.
that kind of semantic information to that. Yeah, I think so. I think where it will come into play the most is if texture is important, and that's something that your depth information doesn't pick up quite so easily. So if it's slippery, this is not something that your depth camera can know. And if, for example, your color information is giving you some additional information about whether or not it's a rigid object, or if it's squishy, if it's slippery, or if it's rough surface, that I think can definitely help. The other place semantics obviously comes into it is if you're targeting a specific thing. So to be able to say grasp the can, you need to know what can is. And the only way that you can know that is by having semantics built in.
And the final online question is, recently there have been some presentations on non-human intelligence based on biological designs to create AI, as the brain of an insect has finally been mapped out successfully. Is it known if it has been in combined development with other systems and AI automation design, such as biological AI focus?
Yeah, there's a whole field of people who work on this specifically. So insect robot hybrids are out there and they exist. And they've actually existed for a long time. One, because people are curious and want to know how it works, but it feeds in both ways. So robotic design also takes a lot of inspiration from biological design. So partly is understanding the mechanisms of how insects, other mammals and things work, and trying to put that into the mechanism of a robot. The other thing is whether or not you can really have synergies within a single symbiotic system. This I don't know quite as much about, it's not as close to my field, but definitely every once in a while you see an article pop up, which is like, okay, there's a cockroach with a computer stuck into its brain and they're trying to navigate it through space. So definitely there's like entire groups of people who are working on this. Very interesting field. A lot of it is looking at how you can exploit the benefits of the biological system, which is extremely complex and extremely well engineered after millions of years of evolution to do sensing, perception, and scene understanding very, very well. On the other side, we can't convince a cockroach to turn left or right without specifically putting a controller and attaching that to the system. So therefore, trying to kind of bring those two things together is kind of where some of those areas are going. But personally, I find that the kind of biologically inspired stuff is the very interesting things out there.
Cool, thank you. Were there any questions from the audience? Yes, let me come up.
Hi, thank you. I'm Chen. I have a question. I heard there's already some ChatGPT API. Can we just import the API into the main node of the? We don't need to care about all these things and just ChatGPT.
Does ChatGPT solve everything? It's a good point. ChatGPT is amazing, and I think it does some really cool stuff. What ChatGPT is currently still struggling with is embodiment. So ChatGPT, if you have kind of read how it works, trained on natural language processing, it's poured through tons and tons of text. And as with all kind of deep learning, it's pattern recognition at the very, very core. So the fact that there's so much data out there on how we use language means that ChatGPT has been trained on heaps of examples. So it's very good at language, extremely good. Extremely good at understanding contextual information, which is described in language too, which is pretty great for the kind of area that we're looking at. What it cannot do for us just yet is to turn that understanding into a physical action in space. So it can say, I know that to pick something up, it means that it will end up in the hand. But there's nothing that will turn that into an actual command that goes into the robot, a voltage or whatever it happens to be, that's actually going to go and execute that. And one thing is about kind of predicting forward to infer how something should happen, but how do you actually then fold in that live experience? So when the robot is really there, and ChatGPT or whatever is saying, okay, in order to make this cup of tea, I have to first boil the water and then do all this kind of stuff. What happens when something fails, right? How quickly can it react to that? How does that fold in the live information of the robot interacting in that scene to update what ChatGPT understands about the way that its commands are going to come out next? So I think there's a lot of very cool stuff also coming out of these gigantic tech companies. So Google, Facebook, OpenAI, they're all fighting each other, trying to solve this thing first. And they have the thing that is really kind of the blocking point is who has access to the most resources, physical resources, to get the kind of data that ChatGPT has access to on the web, but get that version of that where there's actually a robot in the loop. That's extremely hard. And also, how do you process that data as well? That stuff is still extremely challenging. So I'm excited because I think ChatGPT is going to be an amazing entry point for a lot of this work, but there's still tons and tons of work to do as well.
Oh, yep.
Oh, hold on. I'm curious about how much crossover there was in the behavioral sense with the interaction planning and whether there's an element of interacting with known people and so on. Could you tell us about that?
Yeah, so for this work, no, because we were really just at the very start of this. And what we would like to do is to actually learn, or at least regress, what the parameters of our transition models and so on were, rather than just have us kind of make it up, which is how we started off. So when we talk about that Monte Carlo tree search and the formulation as a POMDP, all of those kinds of parameters were stuff that we just kind of picked because we observed it kind of happening that way. So like, what's the chances that somebody lets the robot through after it does a say action? Oh, it's about 80%. Okay, let's make it 80%. What would be better, of course, is if you actually used all of the live experiences and updated those parameters online. Now, we never got quite so sophisticated as being instance or individual aware to say, I've seen this person before and I know that they're very cooperative versus somebody else who is not. But certainly you could imagine that being built in, or at least doing typecasting, for example. Now these ideas move more in the direction of agent-based reasoning and navigation. So again, this is moving into a more, another gigantic field of people who look at agent-based methods. But specifically for robotics, I think it's quite interesting because we are still at the point where robots are novel. People are kind of curious as to what happens. Who knows what it's going to be like in 10 years or 20 years? Maybe we're bored. Like, cars, we don't stop and stare at cars anymore. But the first time cars appeared, people were very curious about them and it changed the way that drivers could behave. I feel like there will be some shift that will happen as we start to see more systems like this moving into our daily spaces. I think the novelty will wear off and perhaps some of these challenges will vanish. If people stop caring about the robot, it maybe has a much easier time navigating through people. But we are yet to see, and we have to make it across that barrier first.
Are there any more questions? Awesome. Give another round of applause, please.
Thank you very much.
And we've got a mug for you for coming
Thank you very
through.
much.
That's okay. Thank you for coming, giving a talk. We appreciate it. We have a Mechatronics panel on Thursday. If you're interested in coming, check that out. A few different groups. Pizza's on the way. Domino's lost 5 pizzas. We're not sponsored, so I can say that. But yeah, so pizza's on the way. We'll have food soon. But thank you again.
Thanks very much.
It's been lovely having you.
All right.